Hi everybody, here is movie number 1 from chapter 14. I'm going to do 2 of these, first of all because we have a 15-minute time limit on YouTube, and secondly, I want you to see, kind of get these broken out into order and how they go. Alright, so in chapter 14, or 13, sorry, 13 rather, we are going to look at what's called bivariate data. And it sounds worse than it is. But all this is are data that is in pairs, that is x's and y's. So those are just points on a plane. Alright? And up to this point, with the exception of the times that we were doing correlation, we were just looking at data in one dimension, just in x's. So now we're going to look at data in x's and y's. And actually what we're doing is an extension of the correlation that we were doing from the previous sections. So this is pretty interesting, and it's kind of a shame that we save it till the end, but that's the way it goes. Alright. So when we have bivariate data, you can think of data that looks something like this, and you think, gee, you know what? I could picture a line that falls kind of close to this. Now, not all the points are going to fall on there, but they're going to be pretty close. Some of them will, some of them won't. But it might be something like this. And that would be pretty good because I could use that for forecasting and such. Okay, and that's exactly what we're going to do. Now, I know you're going to be devastated. We are not going to be working them out by hand, and I'm not going to be going through the derivation. Again, that involves calculus, which should send most of you running, screaming from the room when I use that dirty word. But you're safe. So what we're going to be doing is using Excel printouts that actually do the numerical derivation for you. So you look at this and you think, that's a line, and you cast your mind, you cast your mind back to your algebra days, and at one point in time, you learned something like y is equal to mx plus b, yes? I hope you did. And m was equal to the slope, right? And b was the y-intercept. Okay? Well, we're going to be doing that, but it's a lot fancier now because we're grown-ups and such. Alright? So this actually is referred to as simple, and simple is relative, I know. Simple least squares regression. And it has a very interesting history, which you won't get to hear anything about. But there's a nice course in regression. If you get a chance, you should take it. Okay, and the theoretical model, again, this is purely theoretical, is equal to, y, the y variable is called the dependent variable, is equal to beta 0, hang on a second, plus beta 1x plus an error term, epsilon. Okay, now don't get all freaked out with the little Greek letters. Remember, this is theoretical. This isn't the world where we have all knowledge. Well, guess what? We don't. All right, so that being said, we're going to get a sample and we're going to have what's called a fitted model. And this is going to be y hat is equal to beta hat 0 plus beta hat x, and the epsilon term, beta hat 1 x, and the epsilon term drops out. Essentially, it's like taking an expected value. It's like taking a mean, and the mean of that is 0. That's what happens to it. Now, before you totally flip out, the beta hat 0 is your y-intercept. Aha. And the beta hat 1 is the slope. Yay. Okay? And we're going to just read those off of printouts. So it's pretty good. All right? Now the key to remember about this is linear relationships. So you have to keep that in mind. And let me draw a couple pictures for you. Let me change out the... All right, so again, let's do something like this. Make those points look... So if I have something like this, you can kind of visualize a line going something like this. If I have a bunch of points going like this, you can visualize the slope going, a line going something like that. All right, linear relationships. Now, suppose I have a bunch of points going like this. There's definitely a relationship between the points, but it is not linear. Therefore, regression is essentially meaningless in a situation like that. Okay, so you wouldn't even try to run a regression on something like that. Okay? Good. All right, let's take a look at something. Let's see, is it this one? Yes. Okay, I have a file from Dropbox, and we're going to take a look at something. Just hang on a minute. I'll show you some more pictures from my last vacation. Come on. I was kidding, by the way. I'm not really going to show you. Keep going, keep going, keep going. Why isn't it going? Huh. Sorry. We're getting there. Here's my dog who's gone to heaven. Okay, it should be around here somewhere. Here it is. All right, so on the first page, yes. Okay, there are my X's and my Y's. This is just made up data. So there are the X's, 1, 2, 3, 4, 5. There are the Y's, nothing too interesting. Then, the next page has the actual output. This was done in Excel, and I kind of squished everything together so you could see what it looks like so it'll fit on the screen. But the important stuff is as follows. Okay, so here are the coefficients. Here's the intercept. It's the 209. So if I ask you, what is the least squares regression equation? You would write down y is equal to 2.09 plus, and then right below that is the slope, 1.81 times x. Okay? That's all there is to it. All right, that's the equation. Then, all right, remember we did the correlation? That's on there. That's up at the top. That's where it says multiple R. So that's the 0.9864. Now, something that's more important in regression is the r squared. The r squared is the percent of variation that the I should say the percent of variation in y that the model explains. And in this case, it's 0.973. It's actually the r, literally the r squared. Don't worry about the adjusted r squared for our point. Okay? Alright, so for the warm-up movie, that's all we need to know right now. And we'll get to some of the other stuff in the next movie. Thanks!